Welcome back, everybody. So I told you that, well, actually, this is my least favorite lecture of the semester because I have the feeling I'm just throwing things at you, like throwing all these tricks at you. But let it serve as inspiration on how to build systems and how to make these systems even faster. Anyway, I would like to, because of the clustering, I'd like to come back to this SQL extension. Because of course, the reason why we are doing all of that, all of these slides that I showed you with the tricks, is because some people, engineers, are working very hard in such a way that nobody has to go through this. And the people that do not have to go through this, they can just write SQL and create their indices and create their tables and create their vectors and use their queries, and everything will just be magically fast. So you've seen in the DMDB normally that you can make your SQL queries fast with indices, right? You remember that you have hash indices, tree indices. Who remembers this from the database lecture? Most of you, right? It turns out that we can also build indices for the vectors. We can also have indices. And I'm going to briefly go over two of them to show you what it's like. But first, in the SQL syntax, for the people who have the luxury of writing SQL and don't need to worry about the details, it's just 2 lines of code. They just say create index on the table using one of several indices. So there's 2 of them that I'll show you. So HNSW, hierarchical navigable small words, is one of them. So you say which kind of index you want, and then the column that you want to index, and then the operations that you want to index on. So you remember you can have the L2 distance, the L1 distance, the cosine, Hamming, Jacquard, and so on. And so you have plenty of them to pick from, depending on what you want to index on. And then once you have an index like this that you have built, then the queries that I showed you earlier, the select from where using the distance, is going to be super fast, because that's exactly the goal of the index. All right, so 2 of them that I very briefly go over. Let me start, they have very strange names. So let me start with IVF flat, which basically means inverted file with flat compression. The idea is still this clustering. You remember the clustering? The idea that you basically group the documents by clusters in this way. Sorry, I went too far. So what you're going to do is cluster the terms, and then all of those that are similar are in the same region. And then you query, whenever you have a query, you look at the cluster in which you are, and then you look at the documents that are in this cluster, a bit simplified. And so the index provides you an efficient way to directly access the clusters and the associated list, right? So that would be IVF flat, so connected to clustering in this way. But that's all I'm going to tell you, because otherwise after it's too advanced. So that's the IVF flat that uses this idea of clustering. And the other one, in fact, I would connect it to the skip pointers. You remember the skip pointers that we used to quickly go through a postings list when there's a lot of documents that do not match? Well, in fact, the second index is a generalization of skip pointers in a way, where you have some kind of layers where you have all of your documents in here. For example, you have let's call it a small path, right? That where you have to go slowly over them, and then you have a highway, you have the train, and you have the plane, right? So this is the fastest route, and every time to go to an upper layer, you remove documents, right? That is the idea of the skip pointer, right? The skip pointer directly skips to a document farther away. Well, the idea, the difference between the skip pointer is that now we have multiple layers of skip pointers, right? We have the small skip pointers, medium skip pointers, and very large skip pointers. And so the idea is that you can go down or up in the layer that you wish. If you are on the upper layer, you will have a lower recall. Going to very quickly come to the recall and precision, but I've already explained that at the beginning of the semester. So you're going to have fewer results. And if you go down, then you have more results. But the idea of this is that on the fast lane right here, on the highway, you can very quickly navigate close to where you want to be, and then you go down, and then you see what you find locally. That's really just like taking the plane to let's say, Vancouver, and then you take a train to a city maybe a few hundreds of kilometers away, and then you take maybe a bike to go to your final destination. It's exactly the same idea here of a very fast, and then you go down in the layers. That is exactly what this HNSW index is actually doing. It has all of these layers. These are all the vectors, right, that you want to compute distances on, but it organizes them in these layers in such a way that here you have this very fast lane that very quickly navigate to everywhere in the vector space. And once you have gone close to where you want to be, you go down a layer, and then you look at the local documents that you have around you, right? So this is HNSW. Okay? High level, I'm not going through the detail of implementation. So to summarize, IVF flat has to do with clustering. HNSW has to do with skip pointers, but over the vectors instead of over the postings list, right? That's basically the very high level way to think about that. But of course, the reason for that is that nobody needs to think about that because they can just write these 2 lines of SQL and get that for free, and then everything is going to be super fast. Okay, so that is the trick. And now to conclude this series of slides, I would like to now zoom out on everything we've been doing, because we have looked at so many things since the beginning of the semester. And in fact, we have looked at enough things that we now have enough components that we can assemble into a full-fledged information retrieval system. So I just want to show you that, like everything you can do now. So the architecture would start with reading the documents and parsing the documents, right? So for that, we've seen linguistic, post-processing, you know, the Porter stemmer and all these tricks, the tokenization in order to read the documents, turn them into tokens, and then build the indices. Which index? We've seen plenty of them. We have seen the standard inverted index and plenty of modifications of these indices, even the byword index, keyword index, k-gram index, permuterm index, they're not even all here, zone indices, inexact top K retrieval, the tiered positional index that I've shown you as a trick. So typically, you can build several of them. Doesn't have to be just one. You build all the indices that you need, depending on your use case, depending on the queries that you think the people are going to run on your system. Right? So you build all your indices. Now we've seen that in terms of query, we have plenty of solutions. You have the Boolean query language that we've seen at the very beginning. We've seen that we can introduce wildcards. We've also seen how to use indices to process these wildcard queries. We've seen phrase queries, and we've also seen the indices that efficiently process phrase queries. You remember the byword index, the positional index. We've seen the queries that are basically the libraries of the ETH, right? Where you have the title, the author, and you type a term in each one. That's actually close to relational database systems when you do it in this way. And then we have the vector space model, super powerful, super hype at the moment with vector databases, where we have the all of these scalar products to compute. So these are all the queries that you can have in your system. Typically, a system that indexes the internet or a huge collection of books is going to cache the documents somewhere. Why is that useful? Because when you display the query results, you like to show some snippets of the book. Like you show the term and you show around the words that are around the term. That's what you see in a Google search, right? So you still want a bit of a cache of the document somewhere, the indices. Then the query arrives, so you have to parse the query, depending on the query language you use, maybe spell correction. You also know how to do that, the permuterm index, the k-grams, and so on. Also based on the soundex algorithm, you can do some spell correction. And then you can query one or more indices, doesn't have to be just one. You can use all the indices you want in order to return results. And so you are going to score and rank. So you have the intersection algorithm, union algorithm for Boolean queries. We have the evidence accumulation pattern that you have for the scalar products, right? Where you see you accumulate the sum of the products of the TF-IDFs over the terms for every document. And then you have the results to display. You use the document cache to display the fancy results, including excerpts from the documents, right? And of course, all of that might be parameterized, right? You might have some weights that decide how your system behaves, and these weights might have to be trained separately in advance based on machine learning, right? So this is outside of the scope of this lecture, but this is where machine learning can be plugged in, right? You can learn some of the parameters to do that, and that gives us a full architecture for a full-fledged information retrieval system, right? So of course, building something like that is a lot of work. We obviously cannot make you build an entire system like this, but with the weekly practical exercises, the programming exercises, we make you touch a little bit of these things one by one so you get a feeling of how it's done, right? Okay. Oh, I would like to say one more thing because I proceed to the evaluation when I come to that. When we have all of these vectors here, in this lecture, and that's the way it was done in the vector space model, the vectors here represent documents and queries, right? Every point here is a document or is a query. In LLMs, like ChatGPT, it's no longer the case. We still have the vectors, we still have these computations, we still have the vector database, we still have these indices, we still have the scalar product and so on, but the interpretation of these vectors is different. And that's what is called an embedding. Who has ever heard of that? An embedding? Right? So maybe you'll see it in some of you, right? So you'll see it in the LLM lecture. It's basically the idea that whenever you have a word that basically means something, you can represent kind of the meaning in a vector space. And a word is going to be close to other words that mean similar things in the same vector space. But it's actually even more powerful than that because you can even have the directions in which you go that mean something to associate things. Like, I don't know, as an example, king, queen, man, woman, father, mother, and so on. Like it basically associates. You can compute associations in this way that correspond to directions in the vector space, and that's very, very powerful. So it means that even though you have learned these things in the context in which vectors are documents and terms that are basically are TF-IDFs for every term coordinate, this still applies to LLMs, just with a different interpretation. Right? So if you are interested, you can just register to the LLM course and take it from there. It's a very interesting topic, of which I'm not a specialist. All right. Any questions so far? Okay, so let's move on to the next part. You will see it's going to be easier. So let's take it as a small break before we go to the probabilistic information retrieval and language models, not the large ones, the normal ones. Let me stop the recording.